Your mission: travel across the uncharted sectors of deep space. Scan every planet you encounter for signs of life. Avoid asteroid fields and gravitational anomalies that could damage your ship. Good luck, Commander. The stars are counting on you.
For Task 1 and 2, the incorporation of gyroscope sensor and servo motors are made to ensure that there is proper correction when moving in a straight line. The gyroscope will detect if there is any deviating movements made by the robot, and the servo will then be activated to do quick corrections, ensuring that the robot is able to move in a straight line. The turning method chose incorporates a locking of the inner wheel and generating movement on the outer wheel to create a tighter and sharper turn. As turning 90 degrees is important, the ICM motion sensors, which are acting as the gyroscope sensors, will also be used to determine which angle the robot car is to stop at. However, during test runs, it was found that the robot had some imbalances on its traction to the ground, which had to be added to allow the robot to have more traction and consistency in the turns. When a right turn is intended, the back outer wheel will first be activated and move forward, while the back inner wheel would then lock, thus allowing the robot to have a tighter and sharper turn. The same concept is applied when turning left, where the back outer wheel will be activated and moving forward.
Task 1 revolves around Communicate task. In it, we have UR interrupts in the form of commands sent from the RPI, which triggers a callback function, placing commands into a command ring. Commands are then read from the command ring, and the corresponding actions are then taken by the robot. Task 2 revolves around Start Task 2, which can be thought of as a series of infinite while loops broken by RPI UR transmissions. Preset movements are then executed between the loops while sensing tasks take place in the background. These tasks include Start Ultrasonic Task and Start IR Task. A timer heuristic based on the time taken for the robot to reach Obstacle 2 after passing Obstacle 1 is used in the Return to Car Park phase instead of encoders.
I will briefly go through the functionalities of the Android app. At the bottom, we have the map configuration, chat, and challenge buttons. We also have a Bluetooth page that allows the tablet to scan for nearby connections. Next, we are able to manually input the obstacles by indicating the X and Y coordinates as well as its direction.
So next, we can also directly add obstacles on the grid map just simply by a touch. So for example, I can add 3 obstacles over here, and we can also change the bearing of the direction of the image on the obstacle. So for example, here I can simply click south and it will be reflected accordingly on the grid map. So next, we also have the drag function where we can simply just drag the obstacle to shift its position on the map, as well as any drag outside of the grid map would just simply remove the obstacle. So next we'll talk about the 3 yellow buttons here at the bottom left. So the first button will be to save the current configuration of the obstacles, as well as send all the coordinates of the obstacles to RPI at once. And the second button will be to directly upload the last saved configuration of the obstacles, and the third button will be to simply reset it. So for example, I will just reset it now and upload the previous configuration. So then lastly, we also are able to manually control the direction of the robot on the grid map itself. So for example here, by moving up and moving down.
Our algorithm uses A-star pathfinding with traveling salesman problem. It plans the most efficient route to visit all the obstacles. The process begins when users input obstacle positions on the Android app. This data is sent via Bluetooth to the RPI and forwarded via Wi-Fi to the algorithm, where it receives and processes the obstacle information. Our algorithm uses A-star search with TSP optimization to compute the optimal path to visit all obstacles. It then converts the computed optimal path into executable commands, which is sent back to the STM for robot to follow.
Finding the optimal path required balancing safety with efficiency. If our parameters were too strict, path computation became slow or even impossible. If too lenient, collision risk increased. We solved this by implementing a dual distance heuristic using both Manhattan and Chevy Chef's distances from the robot center to nearby obstacles. We realized that real-world performance could differ from the ideal. Problems like positioning issues or camera glitches could happen and cause image recognition to fail. That's why we implemented an intelligent retrying mode. After the initial run completes, our system automatically repaths the failed obstacles.
Firstly, we begin by taking pictures of our objects. They are then meticulously annotated using RoboFlow, ensuring they are categorized for our model to learn from. We then perform data augmentation to expand our dataset. Then, we made use of the many past images from seniors to further bolster our model's capabilities. We ended up with a final dataset of around 23,000 images to train our YOLO V5 model. This model is then plugged into our inference server running both image recognition and algorithm. The RPI will send the images to the laptop, and it will then return a string categorizing the image. The annotated images with bounding box is then staged in timestamp sequence for checking during task 1 and 2.
RPI is the brain of the robot. RPI connects all components of MDP together. For better performance, our team uses multi-threading queues and locks. Movement locks are only released when it receives acknowledgement from STM. For task 1, RPI receives coordinates from the Android, which it then sends to the algorithm from a flash server. It then waits for the Android to start the task. All commands are either STM commands or actions that the RPI has to perform. For task 2, it's mostly the same, except now there's a new set of commands, and without a dedicated algorithm, it knows which command to execute based on how many acknowledgements it has.
Throughout this project, we've grown not only as engineers, but as teammates. Every challenge pushed us to collaborate, communicate, and combine our strengths, from brainstorming ideas to solving problems. Through multiple failures, we have learned to push through and keep going, combining our efforts as a team. This journey has shown us that true progress happens when creativity, teamwork, and perseverance come together. In the end, we even managed to achieve top 2 in our tutorial group and were awarded a prize by our professor.